All right, let's dive in. Today, we're cracking the code on something that can be a real headache in trigonometry, the domain and range. But trust me, by the end of this, you'll see exactly what goes into and what comes out of all 6 of the main trig functions, and, more importantly, why it all works the way it does. Let's get to it.
So here's the game plan. We're going to start with the basics. What are domain and range anyway? Then we'll look at the big 3, sine, cosine, and tangent. After that, we'll flip the script and check out their inverses, which is where we hit a really interesting problem that needs solving. And we'll wrap it all up with the ultimate cheat sheet to put everything in one place for you. Okay, first things first. Before we can even touch trig functions, we need to be on the same page with the language. And that language is built on 2 super important ideas, domain and range. First up, we've got the domain. The easiest way to think about this is, what are all the things you're allowed to plug into the function? It's the complete set of all possible inputs, the x values, that won't, break the math and give you an error. And if the domain is all the possible inputs, then the range is all the possible outputs. It's every single possible answer or y value that the function can spit out after you've given it a valid input from the domain.
Now here's a really cool way to visualize this. Imagine you have a light shining down from the top. The shadow that the function's graph casts on the horizontal x-axis, that's your domain. Now imagine a light shining from the side. The shadow it casts on the vertical y-axis, that's the range. It's a fantastic mental shortcut to see the function's total footprint.
All right, makes sense, right? Now that we've got those definitions locked in, let's see how they play out with the stars of the show, sine, cosine, and tangent. For the sine function, it's pretty simple. You can plug in literally any angle you can possibly imagine. Go ahead, try. So its domain is all real numbers, from negative infinity to positive infinity. But the output? Well, that's always trapped. Since it represents the vertical height on a unit circle, it can never go higher than 1 or lower than -1. That's its range. And you know what? Cosine is basically the same story. Just like sine, you can feed it any angle you want, so its domain is also all real numbers. And its output, which is the horizontal position on that same unit circle, is also stuck between -1 and 1. Easy enough. But then there's tangent. Tangent is kind of the rebel of the group. See, tangent is just sine divided by cosine. And what's the one rule we can never ever break in math? We can't divide by 0. So anywhere that cosine is 0, like at 90 degrees or pi over 2, tangent just doesn't exist. Those are holes in its domain. But its range? Totally wild. It can shoot all the way up to infinity and all the way down to negative infinity. Okay, so the originals are down. We get them. But now, what happens if we try to run the whole process in reverse? This is where inverse functions come into play, and honestly, this is where it starts to get really interesting. And here's the big switch, the fundamental change. With a normal trig function, we put an angle in and get a number out. With an inverse function, we put a number in and ask the question, hey, what angle could have possibly given me this number? The inputs and outputs have totally swapped roles. Now, you'd think this would be simple, right? If the range of sine is -1 to 1, then the domain of inverse sine must be -1 to 1. And if the domain of sine was all numbers, then the range of inverse sine should be all numbers. Sounds logical, but there is a massive problem lurking here. Any ideas what it is? That problem is that this simple reversal actually breaks the most fundamental rule of what a function is. Let's dig into why we have to add some special rules, some restrictions to make it all work again. So here's the dilemma in a nutshell. If you type inverse sine of 0.5 into your calculator, what should it tell you? Is the answer 30 degrees, or 150 degrees, or how about 390 degrees? They all have a sine of 0.5, but a function by definition can only give you one single answer for any given input. So to fix this one-to-many mess, mathematicians all over the world just had to agree. They decided to pick one specific slice of the circle and call that the official set of answers. For inverse sine, or arc sine, the slice they chose is the right half of the unit circle. What that means is the answer you get back will always be an angle somewhere between -90 and +90 degrees. No exceptions. That's the official range. For inverse cosine, or arc cos, they picked a different slice. This time, it's the top half of the unit circle. So when you ask for an inverse cosine, the answer you get will always be an angle between 0 and 180 degrees, or 0 and pi. And for inverse tangent, arctan, we're back to the right side of the circle, just like with arcsine. But there's a tiny, crucial difference.
Notice the parentheses instead of brackets. That's because we have to exclude -90 and +90 degrees themselves, since the original tangent function was undefined at those exact spots.
Whew! Okay, we have covered a ton of ground. We went from the basic definitions all the way to the tricky logic behind those inverse restrictions. Now, let's put it all together in one beautiful, simple guide. And here it is, the whole shebang, all in one place. Just look at the beautiful symmetry here. The range of sine, which was -1 to 1, becomes the domain of its inverse, arcsine. And that restricted range we had to invent for arcsine, -π/2 to π/2, is now its official output. This table right here is your go-to guide for everything we just talked about.
So now you get it. You know the rules of the game. The inputs these powerful functions will accept and the outputs they're allowed to give. But the final thing to really think about is, how do these abstract mathematical rules actually build the world around us? How do these domains and ranges become the sound waves carrying music to your ears, the physics that holds up a bridge, or the computer graphics that create entire virtual worlds? That's where the magic really happens.